Here we go. Yeah,
Good.
Bill, please go ahead.
Ready, we're getting ready. Very good. Great to be with you gentlemen worldwide. This is, I guess you call a domain-specific language, DSL. It's expanding forth into the form of matrix language. So today what we're going to cover is a quick examination of the usual matrix simulation syntax that you'll see in other systems. A fourth appropriate equivalent, the matrix word set. We'll demonstrate some simple operations on matrices and some matrix calculations. First, the credits. I've been using Win32 Forth from Andrew McEwen and Tom Zimmer. At the very end, you'll see that I've written a 70-page manual on this implementation, and it's posted on GitHub. And you'll see the link at the end. I'd also like to thank the European team who updated Win32 Forth in the early 2000s, going up to about 2010 or 12. They've made it so it's contemporary and works clear up to Windows 10. And finally, Dr. Julian Noble, the late Dr. Julian Noble, he died, I believe, in 2008. He wrote the book Scientific Forth, and the key concepts of the syntax and data structures are from Dr. Noble. First, let's look at how to create a float matrix. All of the number outputs are using a floating point in Win32 Forth. So we create a matrix of 3 by 4, and we use a simple word that's create with a little curly brace, and we name it Forth with a curly brace. Everything with a curly brace on it either generates or absorbs a matrix. So we've created that matrix, and by the way, create is done with a builds does or create does. So now that we have the word first, which is the matrix, we'll then apply the operator to it of list. The little curly brace list accepts the structure of the matrix Forth, lists its contents, and here we see that it's a 3 by 4 matrix, and all the values contained in are 0. Here's an example of direct data entry. We want to type in information right from the keyboard, so we write down first with a curly brace, which opens that matrix, and then the little detailed syntax with the brackets, the vertical bar, the closing braces and brackets says accept the following numbers, and we see row, 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 column, column, column. After making that entry, the second line says first with the paren list, and we list the contents, and we see exactly right. The first row is all 1s, the second row is all 2s, the third row is all 3s. So our direct entry is working. Let's automate filling values. This is mostly for testing. We have the operator fill shown in green. So we address our matrix first. We use the curly brace fill to fill it full of integers. And then we use our list operator. And we see now that the matrix has cell values 1 through 12. Again, this is typically used for testing and a quick look. Here's an example of matrix math. We give it the 3 values, the first value, the second value to be entered, and then the third matrix is our destination. In this case, we want to double a matrix. We start with first, we add it to first, and we store it in first. In the green down below, this equivalent in Forth would be taking a variable A, another variable A, add the 2 together, and then store it in A. And we see exactly on the bottom, we now have double the values in each cell, where at the beginning top left we had a 1, now we have a 2, and then we go 4, 6, 8. down to the lower right. It was 12, now it's 24. So we've added the matrix to itself. Note this could be anything from 1 to 3 matrices, which would supply the 2 inputs and the output. Here's a simple transpose. Again, we create the matrix first and we fill it full of numbers 1 through 12. The green list shows that that's how it's currently structured. Then we address the matrix first and then do the little curly brace transpose and list it. And we say now the rows and columns have been transposed. And the first column now is 1, 2, 3, 4, where it used to be the first row. Now here's a traditional matrix syntax, and we'll see how it matches up with what I've done. At the start, we have a C with a 1, 3. So that's our destination. It says take the following information, put it into matrix C, row 1, column 3. The input is taken from matrix A and matrix B. In this case, the input always has a variable name. It designates cells within the matrix, and then some operations done on those values. Here's the equivalent in this format. In the lower portion, it says and also note that in this matrix fourth, all rows and columns are 0 based. In traditional matrix notation, rows and columns begin with 1. In fourth, they begin with 0. I tried to make a dual system that would allow you to switch between the two, and it got hugely complicated and I gave up on it. So I followed Dr. Noble's lead, which is all matrix rows and columns are 0 based. So at the bottom in the green, we see that we say address matrix A. The double braces lets us address the components within that matrix, and we take row 1, column 1. We convert that to an address and then do the floating point fetch. And for the B matrix, likewise, we address within it. We pick rows and columns 1 and 2. The double brace converts that to an address, and we fetch from that matrix. F plus adds the 2 together. We then address matrix C, in this case, row 0, column 2, and F store, floating point store, stores into it. Note that the terminology is more verbose than the traditional input. However, the parsing and the sequence and the logic is precisely clear. So the traditional syntax being very terse, but not clear in the parsing. I've given a sort of a fictitious example here about how complicated it can get. But here we see we're addressing A and B matrices, extracting components, putting them into C. Parsing is not clear, and the order is not clear. So in fourth, we can pick it apart. We see the clarity. In fourth, the A brace gets the address. The double braces gets a descriptor. In that case, the descriptor is address, rows, columns, and bytes per cell. The 2, 3 specifies rows and columns. The double brace gets the storage address. And now we have on the 4 stack the address, and then a floating point operator operates on that address. In a double row situation, we see the green is what you see visible with the A brace. The lower address is what's on the 4 stack. The double braces and the gets us to the row and column. The double brace on the right says give us the address, and finally fetched the floating point fetch gives us on the floating point stack a particular number. So here's the actual code of that word fill, and this is written in fourth. I'll run briefly through it. First, we have an operator do a set up the loop, and we have a double do loop, rows and columns. At the second do, we see dupe j times I plus single to float. This gets us our stored value that we want to store, computes the stored value, and then with the green arrow, we see the portion that is actually doing the addressing within the matrix. Over double brace gets us the address of the matrix. We use a J and I address in row and column, and then the double brace fetch stores into that. So we see that it's clear, it's clean, and it's actually quite brief. The double loop goes rows and columns. At the very end, we have some housekeeping where we have to drop some numbers. So there's our address is filling a matrix with the row column values from 1 to n. This is a D chart of that operation. You can see how we set up the loop. We get the columns and rows, over the rows, and then over the columns, we get the cell number. We store it in the next column. We store it, and then we can move to the next column by column until it's exhausted. Then we go to the next row, and over rows until the rows are exhausted, and then back to the main loop. We drop the value C, and we drop an address. Simple logic. Very forth-like. So some details, as I mentioned before, the fourth matrix is zero base for rows and columns. Words that have the single brace on them are either generating or using a matrix address. This is just a physical address of where the matrix data is located. It's the parameter field of a bills does word. The word with double brace converts that matrix address into its descriptor. This reaches into the create does parameter field and pulls out the address, the rows, number of columns, and bytes per cell. In the floating point matrix fourth, the bytes per cell is always 8. And the words with the double brace, opening or closing, operate on that descriptor, which also depends the fact that the row and column values have been specified. So here's our summary of the words that are available. We can create a matrix, a couple of flavors of that. That's again a bills does word. We have support words, which will list and fill a matrix. These are developed very early, so we can see what the results of our partial work is. The data entry came along second, which allowed me to put in values directly into the matrix. And then manipulation, the classic ones of transpose, invert, determinate, I, and so on. All written in Forth, all quite brief and quite clear. Matrix math, we can add, subtract, divide, and multiply matrix, and then the matrix form of a dot multiply. We have row and column operators, so we can exchange rows, exchange columns. The stack address allows us to manipulate the addresses of the matrix itself. In other words, the dupe bracket will actually retrieve and duplicate a matrix and make it ready for further manipulation. And then finally, cell math. Within the matrix, we can address the components. We do a floating point fetch, floating point question mark, floating point store, plus store, and so on. The work's divided into 4 levels. Level 0 are the internals, the words that you really don't see when you're doing much matrix manipulation. These are the internal words like seeing if you have a matrix that's row and column conformal and so on. Level 1 is doing cell to cell manipulation. These are manipulating actual Forth addresses. Level 2 is manipulation of the matrix by row and column. This is expanding and it's currently under development. Level 3 then is matrix level, where we can create matrix, we can fill, we list, we copy, we can transpose, we can do multiply. And if you're doing analytic or research work, most of your work is done at this level. So in summary, I use MATLAB and a clone of Octave. And about once a year, I come back to a live project. And unfortunately, I have to kind of relearn and refigure the semantics and syntax, flipping back to cheat sheets and to books. The manuals explain each single data structure, but they do not give the overall parsing order. So you have to figure it out by experiment or by having gone through it. Therefore, what I need is a reverse Polish syntax that needs no refresher course. When you read the code, you are reading the exact execution order. And of course, matrix Forth is the answer. Here are two references on GitHub. You can find me by name, Bill Ragsdale, and I've posted the matrix fourth word set. It's amazingly simple. It's only about 80 lines. And then finally, here's the GitHub reference for my Win32 fourth guide. As I mentioned, it's about an 80-page book. It is in Word format, and it is continuing. In that document, you will see many cases where I put a few asterisks and say additional work needed here. So do we have any questions?
Wonderful
Okay.
read. Excellent.
Good.
Yes, thank you very much.
Good.
So are there any questions? Yeah.
Good. We're all speechless, standing in awe. Very good. Thank you.
I have one, sorry, I have one single question. The size of the matrix, is it also included stored in the system?
When you define the matrix, the word create does it, and you specify the size. So if you want a 10 by 10 or 20 by 20, you say 10, 20, create, and the matrix is constructed to that size.
But that values, are they also in the definition that you can pick them up to see later the size of the matrix when you
Yes, if you address a matrix by name, say the example I had was first, put down the double braces and then type .s, you will see the row and column, the physical address, and the matrix cell size. There'll be four numbers in a row.
Okay,
So
that's returned. Okay,
Yeah.
Thank you.
Good.
I also have a question of how do you allocate the memory for the matrices? Are they in the dictionary all the time, or?
At first glance, a matrix looks like a variable because when you execute the name of a variable, you get its physical address in memory, just as you would for a variable. And located at that physical address are its parameters. Its number of rows, number of columns, cell size, and its address. So one might, so addressing a variable gives you its physical name, its physical address. The double braces give you its descriptive parameters.
I see. And this
Very
is
clear, very open, very interactive.
I see. So if you create a matrix, then it's allocated in the dictionary, or do you have some kind of heap that you manage?
Nope. The heap is a big issue. Because in this case, the matrix is compiled in memory and its fixed location, and its dimensions can be altered, but its size cannot. So you can do a transposed in place because the rows and column product doesn't change. In lieu of a heap, what I do is I go to a dictionary space above here and set up a transient storage area. So that transient storage area allows me to copy a matrix from the dictionary into the transient area, operate on it, and then copy it back to the dictionary. This allows me to have short-term matrices of arbitrary dimensions without consuming dictionary space. However, that transient space is only good until the dictionary size expands and the location out here changes. So I go about 100 cells above here, create a simple structure that is, it has a name named transient, and you can do operations. So when you're doing things like transpose and dot multiply, you need those short-term workspaces. But expanding into a true heap structure is a major change into memory management.
I see. Okay, thank you very much. So are there additional questions to Bill?
I have a question, if that's okay.
Sure, go ahead.
Bill, during your presentation, you showed a chart. I'm not sure I'm familiar with this chart. What did you say it was called? DG chart?
You bring a topic warm to my heart. I will try to keep it very brief. I've done several presentations on D charts. They were developed by Dijkstra in about 1972. It is a streamlined form of flow charting, which lends itself to FORTH extremely well. On the Silicon Valley FORTH postings on YouTube, I have a talk posted there on D charts.
Okay, I'll make sure to look that up. So D is for Dijkstra.
Yes, that's correct.
Yes,
Okay.
the first FORTH2020 talk, Bill did also the D charts with us. It was fantastic. I loved it. Who is next now? Sorry,
Okay.
Dr. King.
Exactly.
Where is Dr. King?
He is with us.
Okay, I'm here.
Okay, yeah, you can share your screen, and we're happy to hear what you will tell us about the eForth compiler in C and how the ESP32 force is actually done.
Let's see.